functions and then the transformations to those parent functions, okay? I passed out that yellow reference sheet. Don't write anything extra on that. You may be able to use it on a test or quiz as long as you haven't written extra stuff on it, okay? Yes. Did you guys not get one? Neither one of you? Okay. Say that again? No, that one is not. Which one? 7B we're going to go over for the quiz next week. Okay, let's practice for next week's quiz. Yeah, I was going to have a quiz. Guys, a quiz really fit on Friday. I was going to push 1-7 to next week because it's not on the quiz. But instead I rearranged some things because Friday, I know you're not going to want to take a quiz anyway. You're going to be all hyped about homecoming. But the other thing is we have shortened periods, right? So I moved the quiz to next week. But instead we're doing new lesson Monday, Tuesday, Wednesday, Thursday. And then Friday will just be a work day and the homework check will be due. But I also shortened the homework check, guys. I shortened the homework check so that only Monday and Tuesday's work is on the homework check. Okay? I'm trying to be flexible here. All right, here we go. The quiz that I returned, guys, you can keep. Make corrections, see me about a retake, yes? Everybody good? Okay. Today's lesson, parent functions are a set of basic graphs and functions that you need really eventually to memorize. All right? It is the simplest function in a family of functions. In other words, this is the simplest quadratic, right? And then we start doing things like shift it to the left 1 and down 7. And then we flip it upside down. We do some crazy business, right? Okay, so this is called the parent. There are, on your sheet, the notes sheet, maybe 8 it says up here. I think it said 8 parent functions. I might have put 9 on there. I'm not really sure. All right, the first one is a constant function, which is just a horizontal line. The identity function is the line y equals x, which is kind of the parent of all linear functions. Goes through 0, 0, 1, 1. The quadratic function is just y equals x squared, and it's U-shaped. The cubic is this shape right here. Then we're going to talk about the square root, which is like half a sideways parabola, and this reciprocal function that has asymptotes. And do you remember seeing this one before, the absolute value function? Okay, the V. And everybody's least favorite. Do you remember this one? The step function, okay? Evaluating these causes some students trouble. If it said this, does anybody know what that would become? Okay, it says is defined as the greatest integer less than or equal to x. What is the greatest integer less than or equal to negative 1.3? Picture a number line, guys. Less than means it's got to go to the left, right? What's less than? The temperature drops from negative 1.3. It's actually negative 2. If it was positive 1.3, it would go down to 1, yes? But if it's negative 1.3, it would drop down to negative 2. So then this is not an absolute value. So you'd have 2 times negative 2 plus 7, which would be 3. I think. Did I do that right? Okay. So it is the round down function. Everything rounds down to the previous integer until you get to the next one. Okay? All right, so on our notes. if we have a horizontal line that's up here at maybe y equals 2, that would be a constant function. The identity function would go through points like 1, 1, 2, 2, 3, 3. Okay, I'm just making something up here. It goes through the origin. Sorry, I didn't do a very good job. So far, so good? Yeah, exactly. The Hofbauer big dot theorem was necessary. All right, the quadratic function, not quadratic formula, but besides going through the point 1, 1, what's another point on here? That's supposed to be a 1. Yep. Goes through the point 2, 4. It's not having a constant rate of change. Goes through 0, 0 as well. Sorry, that's not drawn well. So far, so good? All right, the cubic function does go through the 3 basic -1, -1, 0, 0, and 1, 1. But what is the next point up on that graph? It's not a straight line, guys. Oh, that was badly done up there. Let me erase this little piece and try to make it. The next time it hits a nice ordered pair would be clear up at 2, 8, because it's cubed, right? So I haven't drawn it very well. This graph has symmetry where? With the origin symmetry, which makes it an odd function. That's a concept we struggled with on the quiz a little bit. Have we done one that was even? This one was y-axis symmetry, right? So it was an even function. Now, does that mean every parabola forever is an even function? No. If we shift it, it's not going to necessarily have y-axis symmetry anymore, right? If we shift it left or right. Okay, but the parent function itself does. All right, square root. Can anybody give me a couple ordered pairs on that one? Yes, okay, over here, 4, 2 would be an ordered pair. 0, 0, and 1, 1 as well. So the graph is in the first quadrant only, as long as it hasn't been reflected or shifted or, okay. The reciprocal function, oh, I was trying to do those in color, wasn't I? I didn't do a very good job. Anyway, okay. The reciprocal function has asymptotes. They are the x and y axis. If you put in to this function 1 over x, the point 1, you'd get out a 1. 1 divided by 1 is 1. If you put out a 2, you'd get 1/2. If you put in a 1/2, 1 divided by 1/2 would be 2. Okay? The same is true in the negatives. The asymptotes are the x and y axis. It never actually touches either, but you can shift it and then it will have different asymptotes. All right, this one is called the reciprocal function. So far, so good? Absolute value. What does that look like? Yeah, it is a V. I was trying to do those in black and the graph in color, but I'm not doing a very good job. What are some points on that? 1, 1, 2, 2. Yes, -2, 2. Okay. It is V-shaped. on your calculator, when you have to graph an absolute value function, I felt like we did not talk about this clearly last time, so I wanted to give you a second to see where that is. There's two places to find it on your calculator. One is under math, arrow to the right, and it's at the top here, ABS, okay? Math, arrow to the right under the number menu. By the way, we're going to talk about the greatest integer function in a second. That is this number 5. INT is the greatest integer function, okay? Both are under math, arrow to the right. And just to be honest with you, when I'm graphing an absolute value function, I don't usually use that because it is the very first item in the catalog alphabetically. So I just go second 0, and then absolute value is the very first thing that pops up, okay? But if I wanted to use that greatest integer function, I'd have to scroll all the way down to the i's. So those were under math, arrow to the right, the number menu, or the absolute value one is also the first thing in the catalog. So far, so good? All right, the next one up is the greatest integer function. And everything starting at 0 is an integer, and everything rounds down until you actually get to the number 1. So 0.99 rounds down to 0. 0.95, 0.5, they all round down according to this greatest integer function. Then when you actually hit 1, it pops up to 1. Everything rounds down and stays at 1 until you get to 2. And then the graph jumps up to 2. Okay, is the greatest integer less than or equal to x? It is a type of step function, and like I said, I like to call it the round down function. That because when I read that greatest integer less than or equal to x, I get really confused. Okay, less than or equal to, it just means you got to go down. Round down. And one extra one I put on here is the cube root function. The cube root function looks like this. It's a 90-degree rotation of the cubic function. It goes through 0, 0, 1, 1. Out here it would go through 8, 2. Right, cube root of 8 would be 2. Everybody okay? But you have all the parent functions filled in? Are all of those on the yellow sheet or not? The cube root is on there. The greatest integer function is on here. Absolute value, linear, constant, quadratic, square root. What wasn't on the yellow sheet? Is everything on the yellow sheet? The reciprocal function is on there, right? One, 2, 3, 4, 5, 6, 7, 8, 9. Is that how many were on there? Okay, so there's a couple extra ones on the sheet. There's exponential and logarithmic and rational, as well as the 3 trig ones, okay? None of those will be in this chapter. All right, really fast. It says, what's the function absolute value of x? Looks like this. So what can you tell me about these things from last week? Domain, range, intercept, symmetry, continuity, end behavior, increasing, decreasing. Vesma, tell me something. Okay. Jared, tell me something. Riley, can you tell me something? You can pick any of those if you don't know one. Intercept, symmetry, continuity, end behavior, increasing, decreasing. Remember any of that? Okay, has y-axis symmetry, which means it's what kind of a function? Excellent. Volunteer for any of the rest of those things? Sarah? The end behavior, okay. Okay, and I don't care if you write y, guys. Perfect. Both ends are up, yes? Nicely done. What do we miss? Intercepts, guys. Where's the only place it crosses either axis? Is this continuous? Are there any gaps or holes anywhere? Asymptotes? Nope. Did we miss anything? Increasing, decreasing. Yeah, that was one of the struggles on the test last week. Partially because you forgot it was x values. I'm looking for, tell me what x values, what it is, the function is doing on this left side is going down. So that is decreasing on the x intervals from negative infinity to 0. Okay, from the left until it hits 0, it was going down. Then what happens? It is increasing from 0 to the right, or 0 to infinity. This just means the left of 0, it is decreasing, and to the right of 0, it's increasing. But it's x intervals. Okay? It's not very helpful on that graph because the y intervals are kind of doing the same thing. All right. Can we go through these, or do we need to go through these? What's going to be different here, guys? The intercept is still 0, 0. What are domain and range? Yeah, both are all real numbers, right? We talked about intercept. Symmetry. What does this have for symmetry? Origin symmetry. It would be the same if we turn it upside down, right? So that's an odd function. Is it continuous? End behavior is different. What's happening? Left end is down, and what right end is up. Increasing or decreasing? Okay, it's definitely increasing until here. It kind of looks like it flattens out though, right? I tried to do this on the graphing calculator to show this, and it almost didn't really go very well because it switches to scientific notation, but maybe it would be better if I... Here's the cubic graph, guys. If I trace starting at like -2 over here, thanks. I think everybody's here, so we should be able to get rid of these. Yep. Look at the y value, guys. It's at -8, and it's at -7.02. Is it increasing? Okay, even though this looks -1.06, -0.6, is the y value always getting closer and closer to 0? Then once it hits 0, what's it doing over here? The y value is still increasing. Okay? So even though it looked like it flattened out, the y value was always increasing. So this graph is increasing from negative infinity to infinity. Okay? The whole time I was going up, it changed concavity maybe, but it didn't change increasing, decreasing. All right, ready to try transformations. Transformations are all the things you can do to the graph. You can have rigid transformations where the graph stays the same size and shape. What would those include? Flipping it, okay. Shifting, yes? Okay. Non-rigid transformations distort the shape of the parent function. So what would that be? Like stretching it, right? Okay. We're also going to talk about a weird one today called absolute values. Or the absolute values of a function. Okay. A translation, notice, don't get that word confused. Transformation is all of them put together. Translation is a slide. Okay. Translation is a rigid transformation. A vertical translation shifts the graph up or down, and it will be added onto the back of the function. A horizontal translation is added directly onto the x value of the function inside. And that will shift it left or right. All right, so here's your notes. Everybody ready to try this? If you had something like y equals x squared plus 5, what would that do? Up 5. So when you add onto the back of the parent function, y equals x squared became y equals x squared plus 5. This is a shift up 5 units. It is a vertical shift. And that means it is changing y values. If I had something like y equals the square root of x minus 1, what would that do to the square root function? If it became this, it would shift the graph down 1. It is still a vertical shift, guys. If it's going down, what's it changing, x's or y's? Y values. All right. If I had inside onto the x directly, for example, y equals x cubed became y equals x minus 5 quantity cubed. Now, the minus came with this, so even though it says minus 5k is actually 5, so it shifts to the right 5. Here's my generalization, guys. Generally, anything inside the parentheses is the opposite of what it seems like it should be. Minus 5 seems like it should be going left, right? But it's going right. So this is a horizontal shift. Okay, these were all vertical shifts. And this one would shift to the right 5, so it would change x values. So let's see, what have we not done? We did a square, how about an absolute value? So if you had y equals absolute value of x, and it became y equals absolute value of x plus 2, what would that do? Yep, it would change x values and it would shift it which way? Right. Because the original, see it says x minus h. So here h is actually negative 2. So it's shifting the graph left 2. Just remember, when it's inside there, it's the opposite of what it seems. Everybody got their notes? All right, so give me words. What did this, if the parent function was the absolute value, so absolute value is just the parent function, what would a plus 4 out here do? Up. Okay, 4 units up. What would this do in here? Be careful. It's inside, so it's left 3. So this one has 2 things going on. Right 2 and down 1. We okay? Those were all shifts, either vertical or horizontal. So if this, here's my parent function, badly done, okay? What is this one going to do to that? Let me do this one in red. Shift it down 5, so it would cross down here at -5, and otherwise it would be doing exactly the same thing. What about this one? Right 3, so over here at +3 it would cross and be doing the same thing. And this one? Left, if I could write 2, that just looks like some crazy scribbles, right? Up print. Left 2, up 4. So left 2, up 4 means it would be over here somewhere where this point would be -2, 4. We're good with shifts? Yeah, the Hofbauer scale. All right. Another type of rigid transformation, meaning it doesn't change shape, is a reflection. We have to be really careful with these. A negative out on the whole function is actually changing y values, so it flips it across the x-axis. A negative inside here will change and reflect the graph across the y-axis because it is changing the sign on the x values. We are pretty comfortable with one of these. If you had y equals x squared and you suddenly it became y equals -x squared, you're good with that. What does that mean it did? Flips it upside down. We're good with that one, right? So it actually changed y values. This one is more confusing to us, but let me give you an example. If you had the square root of x and it became the square root of -x, that would look like this, okay? It reflects across the y-axis by changing the sign on the x values. This is negative, the square root of -x. The domain here, the domain would be -∞ up to 0 only. Because you can't, yeah, if you can't put in or get out imaginary numbers. Yep. So if I had done this, what would that one look like, guys? That's this way, right? Let me give you a really tricky one. What's that one going to look like? What quadrant is that going to be in? It'll be down there. Okay, because it's been flipped across the x and the y. All right. It'll be flipping out, right? All right, guys, here we go. This is really important. You have to follow the order of transformations carefully. This is how I think about it. If I were to put a 10 into this equation, I would subtract the 1 first, then I'd take the square root, then I would worry about this negative out here, and last I would add the 2. Everybody okay? Order of operations. If I were to put a 10 into this, because of these parentheses, I would subtract the 1, take the square root, then add the 2, and then worry about this negative, right? It kind of is the same thing for order of operations in describing what's happening here. This -1 does what? Yeah, I started to write the wrong thing. Write 1, then the +2 would be up 2, and then this negative on the whole thing, do you remember what that did? Reflects it over which one? The x-axis. Okay, so this is what it wound up looking like. Here's the x and y, guys. Okay, so it went right, up, and then it flipped over. No. Okay, right. It does say that, doesn't it? Reflection over the X. Right 1, up 2. Nope. Oh, right 1. That's because I wrote it wrong, guys. What is order of operations? What would you do, order of operations? You would do the right 1, then what? Then you would do the opposite sign, which is reflect over X. Okay, so you flipped it over here, then you flipped it, and then you moved it up 2. I was so confusing myself. What was wrong? Okay, they said reflect at first, but it's fine to do what we did. You will get the same thing. The order of operations will work. You just can't do the up 2 before the reflecting, which is what this one did. Oh my goodness, glad I was recording that wrong. All right, this one goes right 1, which would move it over here, then up 2, which would move it up here. No, yeah, I can't tell where the axis is. This is messing me up. Here's the axis. Okay, so the original graph was here. Right 1 was here. Up 2 was here. And then it flipped across the X, which is here, and went down here. Whew. Sorry, totally messed you up. I just follow the order of operations. It does make a difference, though. Do you see that those are 2 different graphs, guys? This one is up in the first quadrant. This one is down in the fourth. Okay, so it does make a difference. All right, that brings us to dilations. A dilation is a stretch. Okay, it's compressing or shrinking or expanding or enlarging the graph vertically or horizontally. Again, if it is on the outside, it affects the y values, and it's just like it seems. A number greater than 1 will stretch, between 0 and 1 will shrink. Here's where it gets tricky. If it's on the inside, like this, it's the opposite of what it seems. A number greater than 1 actually compresses the graph, and a number between 0 and 1 actually expands the graph horizontally. A vertical dilation or compression is towards the X, towards or away from the X. Axis. Okay, a horizontal dilation is towards or away from the Y. All right. The notes on the sheet. Oh, I'm going to skip that for the sake of time. When you have a graph only, you can't always tell the difference. Let me show you this. Do you understand that this is the same thing? Those are equivalent, yes? They will result in the same graph. If I made you describe this for me, you would say stretched vertically. This would say a number greater than 1 inside the parenthesis is actually a horizontal compression, or shrunk horizontally. That's because taking this parabola and shrinking it in this way is going to look the same as stretching it up this way. Yes? Okay, because they're the same. So you cannot tell from just looking at the graph necessarily which happened. You can sometimes, okay? If I had this graph and the zeros changed so that it looked like this, I would know that it was compressed horizontally because the zeros moved in towards the y-axis. All right, let's fly through these. When you have a number out here, it is multiplying on the y. If it's greater than 1, it's expanded vertically, so it's stretched up. Like y equals 2 square roots of x would go up, instead of to 1, 1, it would go up to 1, 2. If you have a number less than 1, it will shrink it vertically. For example, y equals 1/2 the absolute value of x, which is one that you can't really tell what happened, but it would look like this. It would be much flatter down. All right, this is where it gets weird. Inside on the function, okay? So this is changing x values. So if you, this will compress or shrink the graph horizontally in towards the y-axis. If you have a number greater than 1, y equals 1/3 x cubed. Okay, it will take that, and here's the normal cubic. This new one will shrink in towards here, which will look like it stretched it up vertically. Okay, this is equivalent to 1/27 x cubed. That's, I'm full of baloney, because what was I supposed to be doing? Yeah, this would be a 3 in here, not a 1/3. It had to be greater than 1. Trying to get through these and I'm not doing a good job. Okay, a number greater than 1 in here is what would shrink it in towards the x. So this one would be shrinking it in this way. It is expanded horizontally if you put the fraction in there. What would that be equivalent to, guys? So this is expanding horizontally, okay? But that is really the same as pushing it down vertically, yes? Okay? So pulling it out to the sides is the same as sitting on it and squishing it down for that particular graph.
So it's like the only time that it's really not like that when it's basically a trig graph. Is that when it would be different?
A lot of polynomial functions as well will do that. The square root, I have to think about that, whether the square root would change it or not. Okay. If I gave you the equation, you have to tell me what it is, what the right words are from the equation. If I gave you the graph, you could tell me either one. All right, guys, we got to finish this last little chunk here. The transformation of taking an absolute value. When you put the absolute value on the whole graph, it cuts off the negatives and makes the y values positive. When you put an absolute value inside, that what it does is it cuts off all the negative x values and it makes the graph repeat so that it has y-axis symmetry. This is really crazy. Okay, so if you have a graph like this, and then if I said this was f of x, and then you took the absolute value of that, what this graph would become is this. It would take all those negative values down below and reflect them over the x-axis. If you had a graph like this, okay, this graph, y equals x minus 3 squared, that's shifted to the right 3, right? And then you took the absolute value so that it became absolute value of x minus 3 squared. What that would do is it would cut off this left hand side and it would reflect the right hand side across the y-axis. So the graph would have y-axis symmetry. Cuts off the left and makes the graph have y-axis symmetry. Crazy business. All right, we're going to continue tomorrow, starting with some examples. So please, you can start tonight, guys. You can start, where did I go too far? On this assignment on page 52, okay?
I honestly feel like I just learned all the things we started with secret math and how it works.
This one?